Now if you actually built this circuit the way it's drawn, what you'd have would be a short circuit straight across the battery terminals, and what would happen would be the battery would get hot and go flat very quickly. So you're not actually achieving anything at all with this circuit, you're simply transferring electrons from one terminal to the other. Let's see what happens if we start to restrict the amount of current that flows through this circuit. We can do this with a resistor. Now, this relationship between voltage, current and resistance is sometimes a difficult one to get your head round. Imagine we've got a tank of water and a pipe connected to it. At present, we've got a plug in the tank, so no water's flowing out of the tank is full. The head of water here is a good representation of the voltage on the circuit. Now, in an electronic circuit, we know the current has to have somewhere to flow. It has to have a continuous circuit from positive right round to negative. But leave that aside for the minute. The plug is working a bit like a switch. Pull out the plug and it's like switching the circuit on. As soon as you remove the plug, then water will flow through the pipe. And it's the diameter of the pipe that determines how fast the water flows out of the tank. Now at present, this is quite a nice large pipe, and so the water current flow is going to be quite large. If we were to restrict that pipe, then that would create more resistance to the water flow. So if you add more resistance, the pipe gets narrower. A narrower pipe won't let as much current flow through. So we've got a head of voltage at the top of the circuit. We've got the resistance, which allows a certain amount of current to flow. The greater the resistance, the narrower becomes the pipe, and so the current is reduced. If we widen out the pipe again, the current increases. Now resistance is measured in ohms. A 1 ohm resistor has very little resistance and lets most of the current flow through, whereas a 10 megohm, which is 10 million ohm resistor, lets hardly any current flow through at all. Now there's a relationship between the resistance of the resistor, the current that flows through it, and the voltage that you get across it. And this is probably the only formula that you'll come across in this DVD. It's a very useful formula for doing all sorts of things, and it's simply this. So the voltage across the resistor is equal to the current I times the resistance R. Now it's a shame they use I for current, but they've used C for something else, so we have to use I to denote current. And I is in amps, which is an awful lot of current, and in reality we use milliamps in pretty well all of our circuits. Now you may remember from your days at school that you can move this formula about. So as well as V equals IR, we've also got I equals V divided by R, and R equals V divided by I. In this particular case, the voltage is fixed and it's coming from a battery. We know that the value of the resistor is, in this case, 220 ohms, and I'll explain how we know that in a moment. So let's, just for convenience, assume that our DC supply is 10 volts coming out of that battery. Our resistor we know is 220 ohms, so it's quite easy to work out now the current flowing through the resistor using the I equals V over R variation of this formula. If you take the 10 volts, divide it by 220 ohms, the answer comes out to 0.045 amps. Now 0.045 amps is a difficult measure to deal with. So if we convert it to milliamps by moving the decimal point 3 places to the right, we know now that there are 45 milliamps flowing through that resistor.